Hello, everybody. Welcome to Webinar Wednesday, hosted by the Concrete Preservation Alliance. My name is Scott McCullough, and as always, I'll be your faithful moderator for today's session. Ladies and gentlemen, we've had a wild ride. Over the past 10 months, we've covered a lot of ground, and like any good experience, it's coming to an end very soon. We have today's webinar and one more in July. And then that concludes our bridge preservation series. We're considering on developing another series on a different topic. Stay tuned for that for more information. But today we're on to surface applied cathodic protection of substructures. Very exciting. So if you've been here, joined us before, the Concrete Preservation Alliance is a growing coalition of organizations committed to advancing best practices in the field of concrete preservation and infrastructure renewal. We draw on our member organizations to host these webinars, to share their expertise and innovative techniques. And we have a wonderful person here today, Travis Marmon with Vector Construction. The first time we've had anybody from Vector Construction join us, which is exciting. These are all our members, as we've shown you before. They span the globe, and they're all committed to saving structures and renewing our infrastructure. Just today, I'm pretty confident you've been to this website before. This is the We Save Structures website, which is the home of the Concrete Preservation Alliance. The events tab at the top contains all of our registrations for all upcoming webinars. So if you registered today, you probably know that. What you might not know is all past webinars are recorded, and the recordings are all posted below the registrations on this page, as well as all slide decks from all the presentations. So it's a good resource for you. I encourage you to visit often. But on to the main event. Travis Marmon is a NACE CP2. He's also a construction project developer with Vector Construction, as I mentioned. We're thrilled to have him here today. Travis has over 10 years of experience with managing projects, operations, business development, and estimating. Travis received his Bachelor's of Science in Concrete Industry Management from California State University, and he's worked extensively in the areas of cathodic protection installation, electrochemical chloride extraction, impressed current, and post-tension structures. So he'll be speaking to us today about covering a little bit of ground. This is the last bridge preservation presentation. The next presentation in July will be slightly different. So we're going to cover some ground and review everything we've learned so far in the past 10 webinars, and then speak to us about surface applied cathodic protection systems. Trav, we like to put a photo of all of our speakers in the field, because as we know, you're not just an office person, you're also in the field doing the work and learning as you go. What are you doing here in this photo?
We're doing some chloride testing for coring for a realkalization project in Oregon.
Very cool.
On a bridge.
Okay, we'll take it away here.
Yep. So I want to thank everybody for showing up. We're going to kind of move a bit faster through the first part of it. We're going to start with corrosion basics, a little review of the electrochemical corrosion protection options. Been exposed to this previously in with some of the previous presenters, but we'll kind of do a once over on those quickly, and then we'll understand the differences between impressed current and galvanic cathodic protection for surface applied anode cathodic protections, and we'll then kind of drill down and do a bit of a case study on surface applied cathodic protection systems. So get started here. So what we see here is typical. We've got on the top left, we've got a corroded pier cap underneath an expansion joint on a bridge. The middle picture there, we've got some spalling. Looks like somebody coated over the top of a spall and spall let loose and exposed some corroding rebar. On the left and the top right there, we have some epoxy coated rebar with some pretty significant corrosion going on. And then in the bottom left, looks like we've got a series of repairs done on a bridge deck. And then finally, another photo of a pier cap underneath an expansion joint. This is very common, and there's a number of different reasons why this happens, but we'll dig into that. So just to review, we've got a corrosion cell in concrete. Basically, in order to have a corrosion cell, you have 4 different elements. You have an anode, a cathode, and a metallic path and electrolyte. When we have corrosion going on in the place of an anode, we have electrons leaving the anode and then going to the cathode. As that rust and corrosion product occurs on the anode, we'll start to see cracking in the concrete and spalling. The dashed lines here show chloride ingress into the concrete, and that chlorides could come from a number of different, or can occur from a number of different places. Marine environment, sea salt spray, de-icing salts from during the winter in the northern climates, industrial processes, and chloride contaminated aggregates, typically in the sand fraction, or chlorides that are cast in at the time of placement as an admixture. That chlorides exacerbate the corrosion cell. As we see here, we've got widespread corrosion underneath the beam, spalling, cracking. It's looking really rough. And again, over here, we've got pitting due to chloride-induced corrosion. When that chlorides make it to the level of the rebar, it destroys the passivating layer over the rebar, and that's a protective layer that protects that's a protective layer that the steel has in the concrete. As that breaks down because of the chloride ingress, corrosion occurs. So we see that we have a problem. We do our repairs. We saw cut out the perimeters of our repairs. We chip out all the bad concrete, clean around the reinforcing steel, and we install a new chloride-free patch. Problem is we still have chlorides in the concrete right next to it. When that happens, we've got this corrosion cell continuing, and typically that spalling and cracking now will keep moving outside of the repair. Here's a good picture of it. So they've done the repair in time. Now we've got some spalling and cracking going on right next to the original repair. In that case, they call it an incipient anode formation or a ring anode of corrosion. And that'll continue. So now we'll go over some of the solutions when this occurs. And they can be broken down into galvanic protection and impressed current cathodic protection. In a galvanic series, what we have is we install anodes into the repairs. Those anodes are made up of zinc. Zinc is a metal that is least noble or more anodic than reinforcing steel. Mild steel's right here. So when we couple these two metals together, the zinc wants to corrode preferentially to the reinforcing steel or the mild steel. Little diagram here is an electrochemical cell. We have zinc, we have copper. The zinc is more electronegative than the copper. We have Acme, we have an anode, we have a cathode, we have a metallic path, which is our wire connecting the two, and we have an electrolyte or an ionic path right here in the salt bridge. So since all these are coupled together, this zinc, because of its least noble or more anodic electrochemical or electropotential, will want to corrode preferentially to the copper. This same thing can occur now with zinc and steel. We've got zinc, significantly more electronegative than steel. Again, we've got them coupled together, but in this case, we've got them in concrete, cast in with chloride saturated concrete. Same thing is occurring. We have our metallic path, we've connected them. We have the ionic or electrolytic path between the two, and we have our anode and our cathode. Whoops. Sorry about that. We'll back up here. So in an impressed current system, it's all the same. We have an anode, a cathode, a metallic path, and electrolyte. Everything is the same. However, we use a DC power supply to provide additional electrons. What that does is it allows the system to work much more efficiently, and typically in these cases, you'll see those on larger treatment areas rather than targeted areas. And we'll get into that a little bit later. So we've got a number of different options when we've got corrosion going on in a bridge structure. This is a bridge that was 2007 ICRI 2007 Project of the Year in Idaho. It's a spandrel arch bridge, and they used a number of different strategies to mitigate the corrosion in this structure. They used a discrete galvanic anode in concrete and joint repairs. They used galvanic encasements with distributed anodes and overlays and jackets. Galvanic jackets in the marine environment, or what was in the water, to protect that. There's also the option to use targeted protection using a type 2 galvanic fusion anode in high areas of corrosion risk. And these are a hybrid anode that operate both galvanically and with an impressed current. Impressed current cathodic protection systems for decks and substructures. We'll get into that a little bit later. And then electrochemical treatments, an ECE or REALC. These are in short duration and they're temporary. So you treat the structure, you remove the treatment apparatus, and then monitor from there. And then finally, we'll get into a little bit deeper and do some case studies on the surface applied cathodic protection using coatings. So incipient anode mitigation. As we can see here, it's a bridge deck. Probably use some de-icing salts. These joints always seem to be a problem area. They've chipped off the bad concrete, removed it. They're cleaning up the bar. They've got their anodes tied in, and they'll cast that back. But there's a high likelihood that all of this concrete here and behind these fellows is saturated with chlorides. We don't want that incipient anode formation to take place. So we put these anodes along this edge, along these edges and repair areas to keep that anode or that additional corrosion from forming. Encasements is a really nice way when you've got some widespread corrosion. Chip off all the bad concrete, install either some new reinforcing and tie. We've got some sausage like they're called a DAS or distributed anode system, and they're long linear anodes that they install on the reinforcing steel. So in this case, the best bet, take all the bad concrete off. So this concrete's full of chlorides. Install some DAS anodes, cast it back, or in some cases you shotcrete. Either or works fine. Galvanic jackets, marine piers. Here we've got some jackets. We install these in tidal splash zones in areas where the tides are fluctuating. You've got wetting and drying from boat traffic, storm events. We've got a lot of chlorides in the seawater. We certainly have some oxygen and it's wet. It's a great environment for corrosion to take place. And in salt water does activate the zinc. It keeps it active and working. So over here, we have some strip anodes underneath the jacket here before the jacket's installed. this fabric will allow the seawater to wick as that tide goes up and down and keep that anode active and protecting the reinforcing steel. You can get these in round or square or any type of sizing. Targeted protection. So in this case, they've got some repairs going on, but now they want to install, or they know that this previous testing, I would imagine, has said, hey, you know, we've got some high chlorides in the rest of this concrete. It hasn't started spalling or delaminating yet. One way to mitigate that future corrosion risk is using a stage 2 fusion type anode. They operate, there is a power source, so when you install them, they will provide a impressed current protection initially, and then as that, after that's complete, then it provides a galvanic anode to ensure a longer life. These are pretty easy to install. They're low maintenance. There's no external power source. That's a very attractive kind of feature, and they're simple to install. Moving on. And then ECE. ECE is a system that's used to treat larger areas typically. This is a temporary system. So we'll install a steel or titanium temporary anode embedded in an electrolyte, typically like a cellulose fabric or fiber, and install that onto the surface of the structure. Then we make some connections. We connect our positive part of our DC power supply to our anode, and our negative to our reinforcing steel within that structure. When we run that DC power source, we take advantage of the negatively charged chloride ion. We've negatively charged the bar. We have a negatively charged chloride ion. Those two negatives will repel one another. Meanwhile, out here, the anode is positively charged, and that's now attracting the chloride ion. So two things occur. We remove the chloride, reduce the amount of chloride ion saturated into the concrete at the level of the reinforcing steel, and then we create a hydroxyl layer around this reinforcing steel. That increases the alkalinity and the passivation of the rebar. I should have touched on that a bit earlier, but when you use mild steel and install it in concrete, when it's new, what's created is a hydroxyl or a passivating layer around the reinforcing steel. That protects the steel, but chlorides do a very, very good job of breaking that hydroxyl layer down. And here's a photo of the electrochemical chloride extraction process. So you see we've got very large hammerhead piers. We've installed the system in this trailer. You've got rectifiers or your DC power source, and then we wet this system down. Typically goes for roughly, on the top end, roughly 60 days. And at the end of that 60 days, we'll test the chlorides and measure the amp hours of reduction. And that'll tell us when the repassivation layer is formed and the level of chlorides reduced at the level of the reinforcing steel. And yeah, it's a pretty good photo there. Now we'll get into the surface applied cathodic protection systems. Cathodic protection is installed on the surface of the bridge. It can be done two ways. There's a galvanic protection system, which we use a metallizing type. And then for impressed current, we metallize, or you can use conductive coatings. They're very similar, but there is some distinctions here that we'll point out. Metallized coatings been used on marine concrete since 1982. Arc sprayed zinc has been found to be effective and efficient to install. It works very well in overhead situations, so bridge deck soffits, parking structures, those types of areas, and it can accommodate some different geometry. It is used at times for historic concrete structures because of its color and appearance. In the late 90s, a humectant technology was developed to improve the performance in drier environments. So a humectant is a liquid that is applied to the metallized zinc after it's installed, and what it allows that zinc to do is to operate a bit more efficiently. With a humectant, it's been shown that humectant enhances the initial polarization over zinc quite significantly. And it does help with providing more uniform current distribution. And then in time, as the zinc the longer the zinc stays on the concrete, typically you'll see a bit of an increase in the bond strength. So we've got the Garden City Skyway. It was built in 1963 in St. Catharines, Ontario. Leaking joints resulted in significant deterioration of pier caps and columns. So just like we pointed out in some earlier slides, we've got some really rough areas. Piers are rated fair to very poor, and they applied arc sprayed zinc to the piers and columns. And this project, 2,000 square meters or 21,000 square feet. So you can see here, got some spalling, delaminations. I'm sure if you went up and sounded it and on aerial lift, you would find more than what's shown there. So what was the solution? Well, they installed some stairway, some false work to get up at, or scaffolding to get at the repairs. Did all the repairs. In this case, the repair materials cured for 28 days before applying the metallizing. It's not uncommon nowadays to see that time frame reduced to around 14 days. It's just found that you can spray it after 14 days if you're using a high performance repair mortar and you're seeing you don't jeopardize any bond strength. So to start, we've got a lot of surface area to cover. So one of the most efficient ways of doing that is abrasive blasting. The objective is to take all the scale, dirt, grime off of the concrete and add a little dimension to the surface of the concrete. Then we use dry compressed air to clean any of the residual dust and blast media away from the concrete. Once that's complete, we install our anode terminal plates. Now, this is a galvanic system, so what we'll do is we'll scan using a ground penetrating radar rebar locator. We'll find the reinforcing steel and we'll drill a hole right over the top of that reinforcing steel, typically an inch and a half hole. And then we'll drill and tap into the rebar. That's what this bolt is. It's drilled and tapped into that rebar. It's a 1/4 inch diameter bolt. Then we patch it back. Once we've installed the bolt, patch it back, protect the threads, spray the zinc. Then we install this plate and then respray over the top of it. These are little plastic anchors to help hold that plate more uniformly to that zinc surface. This is a galvanic system, so the surface anode or the surface zinc, that's our anode. The reinforcing steel inside the structure is our cathode. We have our metallic path. We've bolted it. We've connected the two, the anode and the cathode together, and the electrolyte now is our concrete. So you can kind of see the operation here. They've got some screening up, to keep the debris from flying around. They use zinc wires fed through. Well, we have a metallizing machine. We call it a bridge master, and we connect it to compressed air. You can see the generators here, and then we use a pretty large generator, typically a 25 kVA generator for one machine. We spray it to 12 mils thickness, and then we pull off test. We want to see how good that bond is between the metallized zinc and the concrete, and we'll get typically right around 150 psi. And then in a galvanic system, we'll install a humectant, which is 100 milliliters per square meter on top of the zinc after it's all installed. Got a nice photo here. So here's the metallized pier caps, and you can see it's not a, it's really kind of unnoticeable. It's got a nice uniform color, hasn't stained yet. It will in time a little bit, but it's got a decent look. And based on some of the initial testing, they anticipate getting a bit over 25-year expected service life. This here's a project I've been a part of. This is Yaquina Bay, Oregon. It's right on the Pacific coast. And this is the second time this bridge has been sprayed with metallizing. So this is a common thing for the coastal bridges for the Oregon DOT. They've been at this a while, and they've kind of worked out a lot of the different bugs and kinks on how these systems work. This is a historic bridge. It was constructed in the mid-1930s. The first time zinc was applied to this structure was in the it was in 1992, and now we're reapplying it today. We started last year in fall 2020. So they've gotten roughly 28 years out of that system. This is an impressed current system, so this is plugged into a DC power source. This bridge is large. It's got 300,000 plus square feet of arc spray zinc. And when this bid, I did some checking this morning, and when this went to tender, there was 150 square feet of repairs designated to be done on this structure. So in 28 years, with this amount of metallizing and protecting the concrete and the structure, they're designating 1,500 square feet of repairs. Now, these projects there's a chance that it's going to go over, but it's not a significant number as what they've identified early on in the tender process. And I'd like to read you a quote here regarding metallizing in Oregon. I found it in one of their reports. According to McGill and Scheich in 1997, this is the quote. The arc spray process was selected as it provided a coating that could be easily applied to complex shapes found in substructure surfaces. The gray color of zinc has the advantage of appearing very much like concrete, another important feature for historic bridges. Also, low electrical resistivity of zinc allows uniform distribution of cathodic protection current, and the zinc system minimizes the dead load added to the structure, which is an important feature for older coastal bridges. So with that, we'll move on. Since we're right on the coast and we're in the city of Newport, we need to contain the sandblasting mess and the zinc dust when we metallize. So when you metallize, it does produce a zinc dust or a vapor, and we want to keep that from entering into the environment and into the public. So you can see we've got some pretty extensive scaffolding, and then that's all wrapped and contained. Down below here, we have our compressors, our generators, and everything that we need to power this system. So the metallizing equipment, this is a bridge master, and we have two spools of zinc wire on that bridge master. each spool weighs around 60 pounds and is 3/16 of an inch in diameter. So the reason why we have two spools is we have two lines. We have one wire running in one line, one wire running in another. Both of those wires meet at this tip. They're electrically charged. When those wires touch and they're electrically charged, they short together and start, I don't know, for lack of better word, zapping each other. When that occurs, it gets very, very hot, and then that zinc becomes vaporized. We propel that zinc, that molten zinc that's vaporized, with compressed air onto the surface of the concrete. Because of the zinc dust, this installer here is wearing a hood with supplied air. So it's kind of a significant process here. And then what happens is, as this installer's applying the zinc, the installer is continually moving left and right and up and down and developing a spray pattern. And each pass, you get about 3 to 4 mils of zinc installed onto the surface of the concrete, with a target of typically between 12 and 18 mils on concrete. So at Yaquina Bay, since it already had a system, we had to remove the old zinc system. As you can see in this section here, in this section of slab, it's rough looking. There's a lot of it that's flaked and delaminated and fallen away. There were other areas of this bridge that looked great. The zinc was well adhered and sound onto the concrete. It's pure speculation as to why that's the case, but it likely had something to do with the monitoring system and how the rectifier behaved in providing DC current over the lifetime of the structure. Some areas underwent, more wetting and drying. The zinc got consumed more. Other areas were drier. The zinc didn't get consumed as much. And then over here, you can see I'm installing some zinc onto one of the piers. This case, it's a bit different. So we use a brass anode terminal plate. This is not connected to the rebar at all, because this is an impressed current system. So this is a brass plate. We've adhered it to the concrete. We protect the threads, and then we spray metallized zinc over the top of it. Over here, we've got some guys installing a reference electrode. These reference electrodes go back to the monitoring station and the rectifier, and what they tell the rectifier is that in these different zones where the zinc is installed, how well it's performing, and if it needs more power, less power, what have you. So the modern monitoring and remote monitoring units and monitoring and rectifiers, they all work in a very sophisticated way to optimize the performance of metallized zinc in these situations. Quality control. In this case, it's pretty simple. You see here, they've metallized, and we've got about 16 mils thickness, so that's an acceptable test. We've just put pieces of tape up. We do this every so many square feet or a couple times a day, however it's specified, and it's typically per operator. And what that tells you is how well that operator is installing the zinc in those areas. Over here, once the zinc's installed, we do a bond pull-off test. And we want to see what the PSI is and how well that zinc has adhered to the concrete. We had a real good test on this one at 268 PSI. Impressed current system considerations. So it's layout, there's zone boundaries, there's distribution wiring, home runs, and rectifier location. All of this is important. So zone boundaries, we break these up into zones for a couple of reasons. One, in an impressed current system, if we have trouble, we want to be able to identify what zone it is and then correct any sort of troubleshooting. Makes it easier than 300,000 square feet of bridge if we've got a zone that's 2,000 square feet or 1,500 square feet. We also put terminal plates or distribute the DC current by zone too. And what that tells us is how different zone is performing compared to another zone. If one zone might need more current than another one. A home run is just a way of saying how all that wiring is run back to the rectifier, to the monitoring. It's very important on these historic structures that we select areas where home runs and conduit are out of the way and not visible to the public. It takes, having all these structures covered in conduit is, kind of unsightly. So do our best to try to move that stuff into areas that isn't quite as noticeable. And then rectifier location, you want it in a protected area that won't be flooded, typically an area with good lighting, so you don't have to worry about vandalism. And then another consideration with an ICCP system, because we're providing a DC current to that system, it's important that we remove near surface metals and metals that are tied to the surface of the concrete and the reinforcing steel. We want to be able to control where that current goes and how it's utilized. So let's say, for instance, you have tie wires or form wires that are touching the rebar in the concrete and then terminate on the surface of the concrete. We want to remove those. So typically what we'll do is we'll identify them after we sandblast, clean everything up. You'll see the steel. We drill it out and remove it. Sometimes you'll have areas of very low cover. So bar that's essentially pretty darn close to the surface of the concrete. In that case, we'll put a non-conductive epoxy over the top of it or overbuild it with a low resistivity repair mortar. And then we troubleshoot the shorted zone. So what we mean by a shorted zone or subzone is any area that we know that the reinforcing steel is connected to the metallized anode. We don't want it to be. So typically we'll blow those out with a welder or another form of DC current and then look for the hot spots. Conductive coating, DAC anode. So this is a water-based coating. It's like a heavy build paint that you can use as an impressed current system. A little bit different here. We used a thin platinum wires to distribute the DC power into the system from the rectifier. You can see here junction boxes, electrical conduit. This would be your home run. We've got some distribution runs, and then these are broken up into different zones and subzones. Again, this was an Oregon DOT project. This is just up the road from Yaquina. It's a bowstring arch bridge on US Route 101, right on the coast. This one was designed by Conde McAuliffe, so was Yaquina Bay, opened in 1931. This structure here had a metallized zinc system that was installed in 1997, and the system failed. And I don't know why exactly, but I think it had something to do with how the DC current, how the rectifier was hooked up to the zinc system. If that's hooked up incorrectly, you can destroy the zinc anode. So in this case, ODOT decided to install a DAC anode system. And then we had to remove the existing zinc. Again, most of the zinc was well adhered. What was bad came off quite easy on this structure. So here's the access. Just did kind of a simple deck with some chains coming down to support it. It's actually not too far above kind of the water line there. We did have to remove some of the decking just to go down and install the DAC anode system a little bit lower than what you see here. But clean sandblast, remove the old zinc. We installed new reference electrodes, terminal plates, everything, you know, just like you started from scratch. And here you've got your different zones. So this structure was broken into different zones, six zones, and then with the different subzones by letter. And then where you see the red lines, the orange, green, the different colored lines, those are actually where we installed that distribution wire, that platinum distribution wire for that system. And then you can see the different squares and diamonds here. That's where they have had structure connections, anode connections, and reference electrodes. So the distribution, it's a really thin platinum wire. You can barely see it underneath that mesh there. But what we do is we install the DAC anode coating first in the area where we want to put the distribution wires. Then we put that metal wire on top of it with a mesh, with a fiberglass mesh to hold it in place. And these are little plastic anchors to help hold that wire tight to that anode coating. Once all that's in place, then we coat the entire structure. You can see here, it's kind of an ashy gray color. So this is the whole entire structure that's coated, and we use a sprayer, you know, a paint sprayer. It's quite a heavy duty one, but we install the coating after the distribution wiring is in place, back roll it with a simple paint roller, and of course monitor the thickness, just like you would zinc. So we want a certain amount of thickness of the DAC anode coating on this structure. Once all that's complete, you can top coat it. In this case, they went for kind of a gray color. Now you can top coat this any color you'd like. If you wanted to use white or a darker gray, it wouldn't be a big deal. This coating is also used from time to time in like condos and different marine areas where aesthetically they may want to use a different color. It's kind of an interesting thing about it. And questions?
Great photos and really interesting projects. Thanks, Travis, for sharing everything with us there. We have a bunch of questions, which I'm just going to pull up here. Let's start with an easy one from our friend Jeff Milton. Did you work with Bruce Johnson on the Oregon projects?
I don't recall that name.
I've actually met Bruce Johnson in the past, but I was not on those projects, so I'm not sure. I suspect he was aware of the projects, though. Okay, on to the technical questions here. Maybe the zinc metallizing. How long do you expect that to last, like service life wise, in say a coastal environment versus an inland environment? Sarah is asking that question.
Okay, so for instance, you know, so Yaquina Bay, right? They're getting over 25 years service on that. And that's an impressed current system. Those systems are going to run, an impressed current system is going to run certainly a bit more efficiently. And so 20 to 25 years, not out of the question in that case. You get down into Florida where you've got a lot of hot wetting. Your metallizing may only last, you know, 5 to 7 years. In that case, you might be better off using a jacket or an encasement. But oftentimes, if your joints are maintained, so you don't have a bunch of salt water dumping down onto your pier cap, it's not unreasonable to say 15 to 20 years.
Okay, actually, maybe this is a good follow-up question from Sarah. She had submitted two back-to-back. The impressed current systems seem complicated. When would you use an impressed current system over a galvanic solution when it comes to this metallizing, like the Yaquina Bay job versus the, say, Garden City project that you showed us?
Great question. So when an impress current system, they are a bit complicated. The technology has advanced quite a bit over the last, I mean, even 5-10 years. The Yaquina Bay project is an interesting one in that the scaffolding, the access to get all of the compressed air, the power out there to perform the work is a significant undertaking. So in that case, right, one way to look at it is, well, if you're going to have to go out and reapply it, how often do you want to do it, and what's the associated cost with that? So typically you'll see these monitored systems and an impressed current system used in situations where access is much more difficult or significant. If it's a pier cap, say under a bridge in, the upper Midwest in Canada, not in a coastal environment, you can drive up to it. It's very hard to make a compelling case to use an impressed current system when you can probably pretty easily just reapply it every 15 to 20 years as needed.
Awesome. There's a question from Anonymous, someone very shy apparently. What are the options for making steel connections between the zinc on the surface of the concrete and the rebar? How are the rebars that are not in direct contact protected? I assume they all have to be connected, yes?
Yes. So there's before we install the zinc anode, whether it's a galvanic system or an impressed current system, what we do is what's called a continuity check. And that's where we'll select random bars throughout the different structural element, and we'll check to see if they're actually electrically continuous using a high impedance multimeter. Typically, you'll find that it's easier to install rebar by tying it to other rebar. However, a lot of these older bridges, it's not uncommon to find a stray bar from time to time, and we want to identify those and then electrically connect them to the other reinforcing steel. But you don't really see that too often in more modern structures. Typically historic structures, you'll find stray bar. But okay. Yeah, great question.
So going back to the beginning of your presentation, I'm jumping around a bit, but Sergey is asking a question. Can ring anode corrosion be caused by a low pH of existing concrete without chloride contamination? If yes, what is the pH level that would trigger that?
So if you have carbonation, which typically occurs in low, not always, but typically in lower quality concrete, maybe concrete that had a higher water to cement ratio when it was initially installed. What'll happen is that concrete will take on a carbon dioxide molecule and create a calcium carbonate. As that calcium carbonate is created, or it's carbonating, that'll drop the pH of the concrete. When that happens, you can get extensive corrosion happening, and I think that pH is right around 7 or 8. It may be a bit higher than that, but or I mean 8 to 9. But I'd have to look.
Okay, no, that's excellent. And just a question from Adrian about the ECE system, the electrochemical chloride extraction system technology you've mentioned, about hydrogen embrittlement. Can you speak a little bit to that? Is that a risk with regular reinforcement, or is it just high tensile steel?
That's a good question, and we do encounter that. We encounter that in like seismic retrofits on like a historic bridge. So in that case, yes, what we do is we identify where so you can create hydrogen embrittlement by using an ECE process on unstressed steel. What we'll do is we'll we'll identify those locations and isolate them from the ECE process. And if the owner wants or elects to do this, what we'll do is we'll install a galvanic anode in those areas to provide some level of protection to those PT areas.
Okay, the questions are flowing in. Another question from Sergey. I have to interpret this, but how dense of a grid pattern is required? I suspect he's referring to the zones in the.
Yeah, zones are typically 1,000 to 1,500 square feet, like on your larger structures like that. When you get into like pier caps and columns, we'll break them up and we'll say maybe the pier cap is a zone or a structural element, and then we'll install our anode connection plates that way. And we like to have redundancy, right, in our anode connection plates.
Okay. Another question from Anonymous. This is a really interesting one. Is there any consideration of integrating this kind of system with a fiber wrap system for strengthening?
Not to my knowledge. If you have like a metallized zinc system on the surface of the concrete, and then you wrap that with an FRP, what you're doing is you're removing the oxygen from that system, so the zinc, won't really probably work all that well. However, what I'm starting to see now on some of these bridges is putting galvanic anodes in the repairs and then wrapping with an FRP, and that seems to be working quite well. So we've metallized outside of the FRP, like next to it or adjacent to it, but underneath FRP, I haven't seen that. Okay,
Azita, and I only know one Azita, so I think it's the Azita I know. Welcome. Is there an environmental concern with applying the zinc spray in bridges over water?
Yes. Yes. So typically, vaporized zinc, any vaporized metal into the environment, it's not a good thing. In the Yaquina Bay project, for instance, there's tourists. There's a restaurant right next to the bridge with a big beautiful patio where people are out dining and spending time outside. What we do is we'll isolate a cell or a work area, and then we have positive and negative air in that kind of cell, so that as they're either sandblasting or they're metallizing, that dust or that zinc vapor is then collected, that air is filtered, and we keep it clean that way. But yeah, it's a big issue. There's again a lot of really great technology out there to help mitigate and deal with these kind of environmental controls and considerations. Other areas of the country, or it's just not that big of a deal. But on the coastal environment, yes, always.
Okay, great. More questions are flowing in all the time. We have only a couple more minutes here, so really interesting one. Maybe can you speak to the benefit or the potential for using the spray metallizing system on reinforcement if it's epoxy coated? Again, the questioner suspects that the insulated property of the epoxy would seem to negate the possibility of creating this electrical circuit.
Yeah. But what you often see in epoxy rebar, right? If that rebar is damaged, if you do have an ingress of chlorides, and it's one of my first slides, where you see the epoxy rebar and it's all, there's all rusted up. What happens is that where that epoxy coating is removed, you typically have an accelerated corrosion in that area. And you don't really know where it's at, right? If it's cracked and water's getting in there and chlorides are getting into area where that epoxy rebar is damaged, what you'll So one way to kind of protect that would be to use a metallized system. That metallizing will work to whatever's exposed, I guess, for lack of a better word. And it will probably last a bit longer in that case, right? Because it's not protecting as much surface area of the reinforcing steel. It's only the reinforcing, the surface of the reinforcing steel that's damaged or the epoxy coating is gone. That's my take on it. In the past, when we've opened up bridges with epoxy rebar, it's not uncommon to find that a lot of that rebar is damaged, or a lot of that epoxy coating is flaked or missing or in rough shape. So.
Gotcha. Okay. Just time for the 2 more questions. I'm going to ask one question of my own, but I'm just going to pick one of the last ones here. This is interesting. For the discrete anodes that you'd put in repairs, what is the typical size, like range of protection, the area of influence around that repair perimeter that you put them in? And how do you, what would you do about the other areas further away from that are also corroding or have high corrosion potentials? Is this metallizing solution an option in this case, to spray over all your repairs and not do the whole element?
So the question is, what's the spacing of the anodes around the perimeter of a repair?
No, correct? Sorry, the first question is, how far does the anode protect into the parent concrete? Around, yeah, what's the range of influence?
Okay, it depends on the density of the steel, right? And we've got a lot of different anodes you can size to that, but you know, it varies in a range between, I don't know, 6 to 18 inches, I would imagine, depending on the density of the steel. One advantage of metallizing, right, is when if you spray like a whole bridge pier or a whole element, and it's got chlorides in it or active corrosion going on, you know, throughout that structural element, that zinc will work very efficiently, and so why it's good to install it's good to install anodes in targeted repairs, but if you know that there's active corrosion going on in the rest of the structure, right, and you metallize all of it, what that does is it's called zone circuit resistance. So the lower the zone circuit resistance, basically the more zinc that's sprayed on the surface of that, the more that zinc will work more, or that zinc will work more efficiently. I don't know if I answered that question correctly, but.
It sounded good to me. You know what? We're basically at time, so I apologize to everybody who submitted a question that we did not get to, but I have a solution for you. I know Travis would love to hear from you, and I just popped up his information on the screen here. So if you'd like to shoot him a question via email, it's travism@vector-construction.com. I'll leave this up here for a quick second so you can jot down his email address. So coming up, as I mentioned, the very last in our series of bridge preservation webinars is Garth Follis on July 14th, speaking about culvert repair using geopolymer mortars. It should be very exciting, and we look forward to seeing you there. This concludes the webinar. Thank you very much for joining us, and I want to say a special thanks to Travis for sharing his knowledge here with us today. It was very informative, and obviously some unique technologies that hopefully our audience can take back and use in the field on projects. So thank you, Travis. We really appreciate it.
Thank you.
And to everyone else here, be safe, take care of yourselves and your families, and go out there and save some structures.